Example comes out of section 11.1, Permutations. The first question is kind of a funny one. It says, if I own 4 pairs of pants and 5 shirts and 3 pairs of shoes, how many different outfits can I wear? I've seen all kinds of different ways of trying to solve this thing, especially when permutations is a new concept. There's anything from drawing diagrams of all these pairs of pants and shirts and trying to draw squiggly lines to them, to a tree diagram saying, okay, I've got 1, 2, 3, 4 pairs of pants. Then for each of those, I've got 1, 2, 3, 4, 5 shirts, 1, 2, 3, 4, 5 shirts, 1, 2, 3, 4, 5 shirts possible. And then for each of those, I have 3 pairs of shoes. Even for relatively small numbers like this, you can see that this little tree diagram starts to have more branches than I really want to manage. The easiest way to do this one is called the fundamental counting principle, and I'll define that for you in a second. But basically it says, okay, I've got 3 things, 3 choices, there's 3 items in my outfit. For the first one, I've got 4 possibilities. The second one, I've got 5 possibilities. And the third one, I've got 3 possibilities. So 4 times 5 times 3 equals 60. 60 outfits would be how many different outfits I could put together. And if you did a proper tree diagram, that you'd have 60 different separate little branches at the end of it as your different outfits that you could wear. So the fundamental counting principle basically just says, if one task can be performed in A ways and the other one can be performed in B ways, then the 2 tasks can be performed together in A times B ways. So it basically tells you to multiply the numbers together. If you're doing pants and shirts, then you have 4 times 5, which is 20 outfits. But if you're doing pants and shirts and shoes, you've got 4 times 5 times 3 equals 60 outfits. The next example says a store manager has 5 people apply for 2 different jobs at the store. How many ways can the manager fill the positions? Again, we could name these people A, B, C, D, and E and say, okay, well, I could have hire A, B for the 2 different jobs. I could have AC, AD, AE, or maybe I don't hire person A at all. I start with B and I say, we could have BA, because the jobs are different. So BA is different than AB, and that the first job might be a cashier job and the other one is a stock person job. So hiring A for stock and B for cash is different than B for stock and A for cash. So we could have BC, BD, or BE, and if we keep going, same idea, CA, CB, CB, CE, DA, DB, EC, DE, and finally EA, EB, EC, and ED. So if you tally that all up as how many different ways you could fill these positions, you've got 1, 2, 3, 4, 5 times 4, which is 20 different positions. Funny that I said 5 times 4 there unintentionally, because a much easier way to do this is the fundamental counting principle. Say, okay, I've got 2 positions I need to fill. If I'm going to fill the first position, I have 5 different people that could go in there. Assuming that one person can't do 2 separate jobs, which is what we do need to assume for this question, we've got then 4 people that could go into the second position. 5 times 4 equals 20. Obviously a much faster way of solving the same problem. Last part of this says a teacher wants to seat 4 girls and 3 boys in a row of 7 seats, but a boy must be seated at each end of the row. Sorry, I scribbled out the and put each there, but we need to have a boy at each end. So one way to do this would be to literally draw out your 7 seats. Simplified would be 1, 2, 3, 4, 5, 6, 7, just 7 spaces. We do need to have a boy here and a boy here. Other than that, we have no restrictions on who must go where. So how many boys do we have? We have 3 that could go in this first spot if we fill that one, meaning we have 2 that could go in this spot here, because if one boy is already sitting in one spot, he can't sit in the other. For the rest of these positions, we just have 5 people left, and so we have 5 times 4 times 3 times 2 times 1. And so if you multiply that all together, you get actually quite a large number here, which is 720 different ways that you could arrange these boys and girls into these 7 seats. I do want you to just notice that 5, 4, 3, 2, 1 situation, because that's something we're going to run into a whole bunch here, and that's the subject of our next example, which is when you see something like 5 times 4 times 3 times 2 times 1, or 10 times 9 times 8, 7, 6, 5, 4, 3, 2, 1, something you do run into a lot in arranging permutation type questions.